Welcome, everybody. Welcome to the 3D AI and Data Technology track. My name is Roop Sani, and I'll be your moderator for this session. In this session, we're going to see teams from the Cesium community share some of the tools and the tech that they've made using Cesium.js and 3D tiles. And this is going to be great for technological inspiration and food for the developer's mind. And with that, we're going to dive right in. Our first speaker is Zachary Sussman, who's the CTO and co-founder of Mac9. Now, Mac9 is a company that builds tools to speed up infrastructure modeling. And today, Zach's going to present how they've built on top of Cesium.js to create a highly interactive browser-based CAD application. So with that, let's give Zach a warm welcome.
Awesome. Hi, I'm Zach Sussman, CTO of Mac9. And today I'm going to talk about the way that we've been building highly interactive CAD tools with Cesium. Cesium's a great renderer, but what it sometimes struggles at is interaction. So we've had to do a lot of extra work to make our user interface actually work in a dynamic manner. This works?
It's coming in and out.
Do you mind if I use the HDMI instead?
No.
Thanks. Cool. And so throughout this presentation, if we're using Slido to ask questions, so if you just want to scan the QR code to ask questions, the QR code will be on most of the slides. So I'm going to move past this for now, and you'll grab that in a second. But to start out by introducing our company, so Mac9 is automating geospatial intelligence by helping land surveyors create maps. So before we get into sort of what we've done with Cesium, I wanted to explain why it is that we're doing what we're doing. Everything in the entire world that is designed and built starts with a map. Whenever any sort of building, any sort of road, the first step in creating that thing is to start with a map. And so when you want to create a map of a construction site, you usually use a device called a mobile mapping system, which, when it was introduced back about 20 years ago, really transformed the field of land surveying, which is the process of creating these maps. Using a LiDAR and a panoramic camera, you can just go drive through an area and collect all of the raw data that is necessary for you to create your map, so you don't have to spend weeks or months out in the field with measuring equipment. But once you have all that data, turning that into a finished map is a slow manual process. For every minute or two that you're driving out in the field, it takes days to process that data into a finished map out in your back office. And so Mac9's Digital Surveyor is software for AI asset extraction and map production. It creates 3D maps of features like road signs or traffic lights or pavement striping from large-scale mobile LiDAR and imagery data sets. So you can go and create your maps. And I'll talk a little bit more about that more visually now. But so this is sort of explaining why we're even building a CAD tool and why we're using Cesium for doing this. Our AI is highly accurate but not perfect, so we need to provide our users with manual extraction tools to clean up their maps and to fill in all the gaps so that they can then go export that into their downstream CAD or GIS software, whether that's something built with Cesium or some other sort of software later down the line. But to explain what we actually do, what we're really doing is we're taking what looks like this. This is just like raw LiDAR data. So it's like a 3D point cloud, which is a common sort of 3D tile asset. We're then extracting those features out of the 3D point cloud automatically. So that way, you can create this final map, which contains all of the various details that you need. We're used across various industries between topographic survey for survey and design applications for constructing roads, or if you're working in like utilities or like telecommunications, when you want to go do permitting and construction for all of your poles or wires or building out new fiber infrastructure, or if you're like a Department of Transportation and you need to go collect where all your signs are to manage your sign inventory. And so just sort of like a flashy thing, and this will explain what we're talking about for the rest of this talk. This is a demonstration of our in-browser CAD application. It's not running live, this is a video, but you can see that you can go in, you can draw all your additional lines or points. Here, what we're doing is we're tracing out a building outline. So we're tracing out basically the outline of a building in a 3D point cloud model. And if you notice, one of the core interactions that we're doing here is we're placing a point in a point cloud. That is a very, very core interaction for us at Mach9 because it corresponds to taking a measurement. Every point in a point cloud is some measurement about the real world. We want to simplify down the very dynamic, very complicated point cloud that we have, which is often like terabytes in size, down to only the most crucial points or measurements. The classic quote goes, the map is not the territory, it's just the most important features of the territory. And we want to be able to pick all of those important features. So picking a point in the point cloud is kind of the core interaction of our CAD software. Being able to say, this is the point that I want to use, not this other point, just this point. This is its semantic. So for example, here a semantic might be building outline. And so how do you do that in Cesium? So that's what the rest of this talk is about, is how do you pick a point in the point cloud? This is not very simple. So our core interaction is to add a point in the map based on something in the point cloud. It's basically the same as taking a measurement. We want to be able to do things like ignore certain points based on their classification. So for example, we want to be able to say, oh, I only want this to pick the ground, or I only want to pick this point that's above the ground. Or there are many points under my mouse. I just want to pick the highest or the lowest. This is, I think, a common feature request. So this is a PR open. We have some questions on the Sandcastle forums that says, hopefully we'll get a chance to implement this soon. Lots of questions. I found this video about how to pick point cloud in Cesium.js in YouTube. Unfortunately, it was accompanied by this incredibly unhelpful comment. Do you have more code? Yes. So if Zhifeng Jin is here, please come see me afterwards. I would like to see your code. So we kind of had to solve this problem on our own. You may be aware of something like sample terrain most detailed. That doesn't work for us. What we need to be able to do is we need to pick it live. So running at like 30 frames a second, I can't make like a network call. I just have to pick the thing. So we went through a bunch of different ways of doing this. Our first attempt was to use the Cesium depth buffer. So when you render a scene on your GPU, in addition to the colors for each pixel, your GPU will also compute something called a depth buffer, the distance between that pixel and the imaginary camera. This is used for things like scene occlusion or culling to make sure that you're drawing things that are behind other things properly, so that things on front show up first. And Cesium has this great method called scene.pickPosition to actually read the depth buffer. So if I click a point, if I click something like pixel, I can go read the depth buffer to figure out, well, what point in the rendered result actually corresponds to that pixel. The issue is that this is crazy slow. There's incredible amounts of lag every time you do this because there's a lot of sort of weird things happening in WebGL whenever you try to go between the GPU and the CPU's memory. So we had to do a lot of workarounds for this slowness. So we basically only use this depth buffer picking method when absolutely, absolutely necessary. So literally only when you were placing a point. Most of the time you're in CAD, you're not actually in the place point tool. You're in the moving around tool, or you're in a drape tool or anything else. So we would only use this point cloud picking, which would drop us to 2 frames a second precisely when needed. And then for the rest of the application, we had to build this entirely separate picking system in the CPU using something called an Octree, which we'll get to in a bit. And every single interactive element, we had to write a bunch of code to have it register itself against our event handler system, as well as the geometry of that. And we basically built this entire separate event handling system, kind of mirroring the way that your traditional DOM works. So you'd have these events. They would bubble up. You could delegate. You can register event handlers. And we still have a lot of this functionality. But it was just a lot of work to build a new tool. And every time you wanted to build a new tool in our CAD application, you had to decide, well, am I going to have to read the point cloud? Or can I get away with just using the geometry? Super, super annoying. So attempt number 2, we were just going to build our own picking system. Just like how we had built our own picking system for all of our geometry-based tools, we were going to do it for our point cloud. So to explain what's going on here, I want to talk about what an octree is. It stands for octuple tree. Just like a regular binary tree at every sort of level of the tree splits into 2, an octree at every level of the tree splits into 8. So you're subdividing all of space into smaller and smaller cubes. So it's this like tree structure in 3D. And what it does is that if you store all of your data in this tree structure, and you want to say, oh, what is the closest feature to this point in the Octree? Without this data structure, you'd have to go through every single point in your point cloud to find out what the closest one is. But with an Octree, you can do it in logarithmic time because you just kind of recursively follow down the relevant parts of the tree. You can ignore most of the point cloud because it's all spatially organized. This is actually what the 3D tile system is based on, is this notion of a hierarchy in 3D tiles is often an Octree. Sometimes it's a slightly different type of tree. But what we did is, so we forked Cesium in order to build an Octree for every single tile that we load in of points. And then to pick array, we would start using the 3D tiles hierarchy tree to find all of the intersecting tiles with the ray, where array is just like something under the mouse. And then for every single tile, we would then use its Octree to pick the points. And so the results of this are, well, we had to build out an entire custom point picking mechanism. So it like spent a lot of CPU power, but it ended up running at about 20, 25 frames a second. We did a lot of optimizations. It was great. It was like super smooth animations, very exciting. But it used a lot more memory. So our clients that were using slower computers started to like suffer from a lot of weird performance problems. We had to do a lot of extra work every time we loaded a new tile, so it made our tile loading a lot slower. Our point clouds would load in much slower than they used to. It wasn't tied to the rendering system at all, and so if we had these like visibility settings that would turn off, let's say, every point above the ground, so you only saw the ground points, this picking system wouldn't know about that. And so when you tried to like pick a point or like draw a new thing, it would like flag, it would catch your mouse on invisible points floating up in the air that you couldn't even see. And finally, one pick per frame was like fine. It was running about 20 FPS. But we have a lot of tools like this digital terrain modeling tool, which basically measures the difference between the point cloud and your topographic map, which had to do thousands or millions of different picks. And that was just still way too slow. So we thought to ourselves, Cesium already has all the points in the GPU. What if we use the GPU? So this is our current approach. We are using the point cloud in GPU for our picking. And so how do you use the points in a GPU? Well, you have to render something. Can we use rendering to pick a point? Yes. In order to pick a point, under the mouse, you have to use the existing kind of visibility settings. You only render the point cloud in this like very narrow context window, using the mouse ray to determine where to place the camera. And then you use colors to encode the coordinates of all the points. And I'm going to walk through each step here. So step one, we configured the renderer to run multiple times. So here's a demonstration of our renderer running multiple times. The big screen is kind of the main render frame. That little debug popover shows that we have rendered the entire scene again using different shaders in the same frame. Then we encoded the coordinates of each point as a color on the point cloud because it's a GPU. It can only render colors. And we kind of decoupled the renderers from each other so that we can arbitrarily configure where to point this secondary camera. Finally, the way that we end up picking a point is we say, OK, I want to pick this point on that curve there. Well, I position a virtual camera top down on that, render a very, very small segment, which you could see over on the right in that picking debugging screen, and then just grab the point in the center. And that's all you have to do. So we have this new API that we built called arbitrary render, which just lets you kind of take an arbitrary one-off render anywhere in the scene. You can set it up with either a perspective or an orthographic frustum, and we do different things with different types of frustums. And then there's this call that's just like get snapshot from camera, which takes in a set of optional transforms that you can just change your scene however you want live, and it'll just output a pixel texture. And so why this is so powerful, well, we don't use any extra memory or compute, because Cesium already has everything that we need already stored in the GPU. Cesium is already rendering all this stuff like 30, 40 times a second anyway. It's lightning fast. It's very parallel because we can render an entire scene at once. And so if you want to pick 1,000 points under various positions instead of just one, you just set up your arbitrary render once and you read off the whole screen. And so it really gives us this new powerful API for grabbing arbitrary slices of a point cloud in a certain frame. And this is going to be very helpful for us as we're building out new features like template matching or like strange sectioning workflows or trying to like render various amounts of topography in these like weird coordinate systems. And so that's where we're at today in terms of our picking system. I'm sure there's a lot of other things happening. But that's kind of what we had to do to get Cesium to be interactive. This is a different QR code. This is a link to our careers page. It'll both appear on the last slide. We are hiring specifically for a graphics-focused engineer, which Cesium Developer Conference, probably somebody here knows graphics. And so happy to answer any questions. Here's our careers page. Let me go ahead and check the Slido for if there's any questions. And otherwise, people can just like ask. Yeah, that's all I have. Oh, and I got disconnected. Yeah, so I have one question, which is, how do you handle the case where there isn't a point directly under the mouse and the pick ray shoots through the point cloud? That's a great question. So we've built out a bunch of different heuristics for this. You can take like larger and larger renders until you find a point. At some point, you do want to be able to find a point. So if you're like clicking to place a point and there's no point cloud point that's within, let's say, like 10 meters or 30 feet of the place that you clicked, you probably don't actually mean to place a point there because there's no underlying measurement of the world that can correspond to that on your map. But we have a bunch of like filtering heuristics and like masking heuristics that we run after this arbitrary render thing. Does this only work with LiDAR technology? So this would work with basically any point cloud. Right now, LiDARs are the cheapest or most effective way to create a point cloud or a 3D model of the world at the accuracies that we typically work with, which are down to like centimeter or millimeter level. I would expect that over the next 10 to 20 years, we're going to see an interesting competition between new methods like Gaussian splatting that let you use only camera systems to create 3D models ever more efficiently and ever more accurately. But then also, LiDARs are also getting really cheap. Like there's one on my phone now, and it used to cost like $1 million a LiDAR 10 years ago. And so it's an interesting race to see who's going to win. Are you open to submitting the better point cloud picking back into Cesium.js? We are definitely open to this. I don't actually know how the contribution mechanism works. That's part of why I'm here, to learn this, to learn how to submit back. We wouldn't have submitted back the like Octree-based thing because it was just so much extra work per render. But this arbitrary render instance is probably something that would be very useful. We did fork Cesium.js to implement both our second and third methods of picking, which is, I think, why it's so great that Cesium is an open library. Yeah. Anything else? Yep. I think if nobody else has any other questions, that's all I have today.